Today, I would like to cover for sure hydroboration oxidation. My guess is that's what we'll spend the bulk of our time on. We'll also cover hydrogenation of alkenes. And then for our little reef session exercise, we're going to cover acid-catalyzed hydration of alkenes. You might have been wondering if you're going to have to know that reaction and if I'm going to show you the mechanism. And the answers are yes and no, respectively. Well, eventually I'll show you the mechanism. But I'd like you to work on it on your own first. I think that will be a useful exercise. My goal here, my agenda, and I don't mind mentioning that I have an agenda, my agenda with the reef session is to prove to you that you already know everything you need to know in order to figure it out. And so that's what we're going to do. And if we have time, if there's like a lot of time left, I might cover ozonolysis of alkenes. I'll leave all of the other oxidation, cyclopropanation reactions, all that good stuff. That can wait until Monday. And then you'll have a bye week from OWL because we were never going to finish chapter 8 this week. Good. So let's see. Maybe I'll just go through the generalized cases of all of these reactions in order. Last time now, you'll recall we covered Oxymercuration Reduction. This is our method for getting the Markovnikov alcohol from an alkene, having it undergo the equivalent of adding H2O in such a way as to give the alcohol product that Markovnikov's rule would predict. And that mechanism also has the advantage, or that reaction in general also has the advantage, of that we don't need to worry about carbocation rearrangements occurring. Why? Because there's no carbocation intermediates anywhere along the mechanism. You can see that for yourself as you look at the mechanism. There's no carbocation, ergo, no worries about carbocation rearrangements, no possibility of that. And we went over this mechanism last time, as I recall. I thought that for a moment that was oxymercuration. Hydroboration oxidation is our method of choice when we want to get the non-Markovnikov alcohol by performing the equivalent of adding H2O across an alkene in such a way as to give the opposite alcohol from what Markovnikov's rule predicts. Sometimes they even use the term anti-Markovnikov alcohol. And I'm kind of anti that term. I'm not a huge fan. I mean, I won't hold it against you if you use it. But the whole thing tends to make it sound like this reaction is an exception or a rule breaker or something like that. And it's nothing of the sort. The reason you get the non-Markovnikov alcohol is fully explained by the mechanism. There's nothing involving any exceptions or any breaking of any rules. But the non-Markovnikov alcohol pops out quite naturally from the mechanism. Like I said, there's a lot to chew on with this reaction, so I wouldn't be shocked if we spend half our time or more on this reaction. Hydrogenation is the addition of H2 across an alkene double bond, and naturally you will wind up reducing it all the way down to an alkane. So this is a method for selectively hydrogenating carbon-carbon double bonds. And we'll find it doesn't touch carbon-oxygen or carbon-nitrogen double bonds, at least in general. And of course, we are only talking about alkenes here. Is it possible to hydrogenate a benzene ring? Answer is yes, but this won't do it. You got to get out the big guns for that. And I think we'll talk more about that reaction probably next term when we talk about reducing benzene rings. Acid-catalyzed hydration is yet another way of adding water across an alkene double bond. In this case, Markovnikov's rule applies because it does go through a carbocation intermediate. And Markovnikov's rule says, of course, that the mechanism's going to be preferred that goes through the most stable of all possible carbocation intermediates. And also with this one, we have to be concerned with the possibility of carbocation rearrangements because we are going to get a carbocation intermediate. And if there's any way for that carbocation to rearrange and make a more stable carbocation, it will happen. And that will probably be the major product. So you ask, well, why do we have to know this one if we already have oxymercuration reduction. Why would you even want to do this one? Well, maybe you have an alkene that will go through a carbocation that cannot rearrange to anything more stable. Then you might as well use acid catalyzed hydration, because then you don't have to worry about dealing with mercury or any of that stuff. You know, much easier to deal with than cheaper reagents. But it just involves adding dilute aqueous acid to your alkene, and it might say H3O plus, it might say H2O, HCl, it might say H2O, H2SO4. There's variations on this. They all mean the same thing. Basically, anything that means dilute aqueous acid is totally fine for over here. And Al will give you some ideas of possible variants that you might see for what you might be given. So again, you get the Markovnikov alcohol, but you have to watch out for carbocation rearrangements. Let's see. And we will, I think it's probably 75-25 that we'll actually wind up talking about ozonolysis next time. But this reaction technically still belongs in this chapter because it is an addition reaction. And the mechanism of this reaction is known. We could learn it, but it is the only one of its kind that we'll ever see in both semesters. Happens to be known as a 1,3 dipolar cycloaddition reaction. And others exist, but it's the only one of this kind that we'll ever encounter, either this semester or next semester. So I don't see any academic benefit to you guys learning it. It's very steppy and kind of confusing, and the thing adds and then it falls apart and adds again, and it's a big mess. So I have a nice little shortcut that I'll teach you. I think I've said there are times when it's totally worth learning a shortcut. And in my opinion, this is one of those times. I just don't think there's any, like I said, benefit to you guys learning this mechanism. I don't think it'll be on the MCATs. Now, if this were an organic chemistry 3 course for chemistry majors, then we'd do it. Then it would make sense for us to do it. Not here. Not when it's the only one of its kind we'll ever run into. Good, so I think we'll mainly focus on these 3 reactions today. And then once again, if you would, as you leave at the very least, please grab your exam. I'd like to give as many of those back as we possibly can. Good, so I would therefore like to switch to our class notes where, again, I've pretty much spelled everything out. As I think I might even have pointed out last time, but bears repeating, if you wanted to make the opposite of the alcohol that Markovnikov's rule would predict, and there might be many cases where you would like to do that, then hydroboration oxidation is the way to go. And it again is a 2-step process. All of these structures and other bits I've explained in the next page, but would it be possible for you to bring the exams on Monday as well for us to pick up? I'll try to remember, but otherwise, see, the reason I was especially interested in bringing them in today was because I'm not going back to my office after this. On Monday, I will be, but I got to scoot home as soon as I teach my 2nd class because my Chem 22 kids are having their exam today and it's online. So I'll try to remember, but if not, then you can always come to my office on Monday. But that's sort of why I was thinking this. Might as well kill 2 birds. Good. No, I mean, I feel bad because it's such a pain for people to get their exams. I guess we're kind of stuck with it. But anyways, so the first reagent that we want to treat with, our alkene with, is essentially borane, which is BH3. And there's lots and lots of different ways that borane is sold commercially. We very seldom use the pure stuff. The pure stuff actually comes as a dimer, B2H6. And you may see that sometimes. I think Owl uses that in some of the questions. And if you wrote B2H6 instead of BH3THF, once again, not only would I not take off points, I wouldn't even notice. It's the same thing. But there's other ways that borane is supplied as a reagent. This is probably one of the cheapest ones. Is there an easy way to separate the dimer? Not really. maybe if you really heated the snot out of it and something like that, maybe, but I think it naturally dimerizes. Though it's, I mean, to some degree, it's in equilibrium with the monomers in solution. So, but the mechanism would turn out to be essentially the same. In both cases, you will, at some small concentration, get the BH3, and that's what's going to be the business molecule for us. But in any case, so the first reagent is borane THF, or the equivalent, and the second step is the oxidation step, and generally this involves aqueous alkaline hydrogen peroxide. So you do need hydrogen peroxide for this. The base doesn't have to be hydroxide, and of course it might say NaOH, it might say KOH, right? Some other version of that. I've done a fair number of hydroborations in my life, and I've sometimes used a weaker base, such as sodium acetate, and that also works fine. So you do need something, you know, at least modestly alkaline in order to get this job done. But it is a two-step process. And again, I'll remind you what it means when we have to write these numbers. What it means is we'll add the borane to our alkene, we'll wait until everything's done reacting and our alkene is consumed, and then we'll add aqueous alkaline H2O2. So that's the way this is done. Or you might see it written with just BH3THF over one arrow and then a second separate arrow that has H2O2 and aqueous base. That's also perfectly acceptable. But that's part of knowing a reaction, and I made that very clear in the class notes. Part of what it means to know a reaction is knowing when it's a multi-step process and when it's just you toss everything into one flask and let the chips fall where they may. So this is not a reaction like that. This is one that has multiple steps. Good, so that means that if we started with this compound, oh, what shall I call that? Those are tricky to name. How about methylene cyclopentane? I can't come up with a better name, though there might be a better name. Instead of getting the Markovnikov alcohol, which would have the OH over here, that's what we would get with either oxymercuration reduction or acid catalyzed hydration, by the way, since that would give us a tertiary carbocation, and there's no way that's going to rearrange. So either of those would work to give the Markovnikov alcohol. But hydroboration oxidation would give us this non-Markovnikov alcohol. And which you would use depends on which of those products you want. And it's very common that you would need one, and it's very common that you would need the other. It's good that we have these different ways of hydrating double bonds because it gives us options and it gives us flexibility. And it means that we could in principle make either one of those alcohols if we were going to take that on to another product. Good. So as I said, a quick understanding of the players here. Borane THF, you might also see BH3.THF, same thing. It's a Lewis acid base complex. And it's almost a shame that THF, sodium borohydride, and BH3THF are almost all mentioned in the same breath at first for you guys. We need to keep those things kind of separate. Because THF by itself as a solvent is certainly a thing that we will use from time to time. And actually, borane THF is sold as a solution in THF solvent. So you can buy, I think it's generally 1 molar in a concentration, 1 mole per liter. And it's not expensive. It's easy to get a hold of. And so if you work it out, this Lewis acid Lewis base complex, you wind up with a minus charge in boron and a plus charge in oxygen. Remember, boron is our unhappy child of the periodic table. It's never satisfied, right? When boron is in its neutral state, it has only 6 electrons around it. It can take on another electron pair to complete the octet, but then it is a minus charge. So boron's never happy. And that's largely why this reaction works so well. It takes advantage of this peculiar tendency of boron to be unhappy no matter what. But this equilibrium is always happening. I'd say the equilibrium heavily favors the Lewis acid Lewis base complex, but you will get some small concentration of borane. And as soon as you do, that stuff's going to react. Same thing someone asked about B2H6. You could write a very similar equilibrium, B2H6, and then the other side, 2 BH3s. Oh, by the way, you'll have fun trying to draw B2H6. But you wind up with some, they're variously called banana bonds or 3-center 2-electron bonds. You wind up basically with some half bonds. You wind up with hydrogens that are half bonded to both borons. And it's a peculiar structure, but it's been experimentally determined. If you want to think of it as kind of a resonance situation, that would not be wrong either. That you could draw 2 resonance forms, let's say. And the real structure is at all times a mixture of those 2 structures. So I've never had the pleasure of using B2H6. It is a gas, so you need to use a cylinder, gas cylinder. It's a pain. You know, you've used the regulator and the hose, and it's pain. I would rather use borane THF. Good. So the other thing I've mentioned here is that hydroxide ion is a more than strong enough base to deprotonate H2O2. Hydrogen peroxide is a little bit more acidic than water. And so I won't say it's quantitative. You know, it doesn't turn every single H2O2 molecule into a hydroperoxide ion. But you do get a high enough concentration when it comes there at the end that we can use the hydroperoxide ion in our mechanism. And that's what we're going to do. So when you see the hydroperoxide in the mechanism, that's where it comes from. And you know the rules by now. Everything shown needs to be shown. Anything not shown does not have to be shown. So I'll show you that when we get there. Anyway, the first step of the reaction is the alkene addition reaction, just like we've had so many of already, in which the alkene, the boron-hydrogen bond adds across the alkene pi bond. And the borane molecule is totally unsurprisingly going to line up in such a way that the hydrogen is going to go nearer the more hindered or more substituted carbon atom, and the boron will line up near the less substituted carbon atom. And I think that makes perfect sense. And that you'll see that right there seals the fate of the reaction. That's what makes us get the non-Markovnikov alcohol. And it's not because we're breaking any rules here. It's a perfectly logical consequence of the mechanism of the reaction. In any case, we at first get an addition product that looks like this. Now, this species still has 2 boron-hydrogen bonds. Just like this species had 3 boron-hydrogen bonds. We still have 2 boron-hydrogen bonds left. Each of those boron-hydrogen bonds, we're going to put this B right where that B is. And each of those BH bonds is going to do the same thing again. Not all at once, of course. First one, then a second, then a third. And so eventually you'll get a trialkyl borane like this. Main question immediately on everyone's mind here is, what do we have to show? I understand that. And I can't give you one particular thing, but I will remind you, and I say this in the class notes, if you look at my old exams, you'll see it's very typical for me with mechanism problems to show you the starting material and the product. So you'll be able to tell what to put by looking at what you're given. If in the product you've added a boron-hydrogen bond once, then you'll show it happening once. If it's happened twice, then you'll see 2 alkyl groups attached to boron, and you'll show it twice. If 3 times, then you'll show it all 3 times. So you will know based on how the question's phrased what you need to put. I kind of have to get that out of the way because I know, and I get it. I totally understand why everyone wants to know that. But please do refer to my class notes here because I cover that idea, the idea of what do you have to put. I cover that pretty well. Good, so this, I did mention this was a 2-step process. This trialkyl borane is what's going to be floating around in the solution very happily until we add the aqueous alkyl and hydrogen peroxide. And again, we're only going to do that after the alkene is consumed. And as I said, there's ways for us to figure that out in the lab. Gas chromatography or perhaps thin layer chromatography, something like that. So we use these things routinely to help us gauge how far along a reaction is. And so that's when we will add the aqueous alkyl and hydrogen peroxide. That's essentially the workup of the reaction. And the first step of that involves a hydroperoxide ion. Remember, we said where that came from. That comes from our aqueous base deprotonating some of the hydrogen peroxide. This is the This is the conjugate base of hydrogen peroxide. Can you see that if we put an H on this O, then you would have H2O2, right? That's the structure of H2O2, or in particular, this here is, of course, the structure of the conjugate base of H2O2. So that's where that comes from. And again, everything shown needs to be shown. Anything not shown doesn't have to be shown. So this is a reasonably good nucleophile. It's got a minus charge in that oxygen. And we already know that boron atoms, trivalent boron atoms, are Lewis acids. They're electrophiles because there's this empty p orbital. In this case, the way we've drawn it here, that empty p orbital is perpendicular to the screen. So that empty p orbital can take on another electron pair. And this oxygen atom with the minus charge is more than happy to provide said electron pair. And so you get an intermediate like this. And then what happens here is a mechanism very, very similar to a 1,2 alkyl shift, such as you might see in a carbocation rearrangement. The idea is that one of these three alkyl groups, it doesn't matter which because they're all the same, will migrate away from the boron and form a new bond between carbon and oxygen. So the carbon-boron bond becomes a carbon-oxygen bond. It doesn't have to look exactly like this. I don't want you memorizing pictures, you know. Owl will put everything facing in a totally different direction anyway. You know how they are. But anything equivalent to that will be fine. And in so doing, we'll do two things. First of all, we'll take the minus charge off of boron. And second of all, we will break that weak oxygen-oxygen bond. That's one of the weakest bonds there is. And that is the money in the bank for us in terms of this reaction mechanism. It's breaking that weak bond, the weak oxygen-oxygen bond, and replacing with a relatively strong carbon-oxygen bond. That's what's going to be the main driving force of this part of the reaction. This does release another hydroxide ion, which we already have plenty of in solution, so it's not unusual to make some more. That will give us this species here. And then what happens is hydroxide ion will again act as a nucleophile onto that boron atom. And nothing surprising about this step either. Again, boron with only 3 bonds lacks an octet, so it's perfectly satisfied to undergo nucleophilic attack by the hydroxide ion. At that point, we break this boron-oxygen bond, and you get this alkoxide ion over here. This is the conjugate base of our product. And by the way, that will happen 2 more times, eventually, to the other alkyl groups that are attached to boron. And you'll eventually wind up with essentially boron with 3 OHs on it, which is boric acid, H3BO3. So it's a water-soluble inorganic species, and that winds up in the waste jug. But all 3 of these alkyl groups will eventually get expelled from the boron atom. And again, you'll know what you have to put based on the structures that you're given. That will make it clear what you need to show. I can't promise which way I'll put it on an exam, but again, if you take a look at my old exams, I think you'll see that I'm generally pretty clear in my mechanism questions. That it's most common for me to show both the starting material and the product, and the directions that I give in the exam are always the same. You need to account for formation of the product shown from the starting material shown using the reagents shown. And I would not be shocked if I used that language, that very language in my old exam. So when you go and look at that, I think you'll see that's the case. This alkoxide ion is again the conjugate base of our product. So we need to find something to put a proton back on it in order to give us the neutral product. Always remember, in general, we're aiming to get a neutral organic product out at the end. So we don't want to stop here at this anion. We're not going to be trying to isolate ions. So that anion needs to pull a proton off of something. How do I know what to put there to use as my proton source? Well, we got to look at what we're given. We've got a little bit of H2O2, probably rather quickly diminishing. And we've got aqueous hydroxide, in which, in particular, there's going to be a lot of water. Water is our solvent here. Heck, probably the H2O2, in fact, for sure, the H2O2 was in an aqueous solution. You know, you can go to the store and buy 3% aqueous hydrogen peroxide. So that's going to be 97% water. There's not going to be any shortage of water. And that's the only acidic species that I see. Remember, water is amphoteric. It can act as either an acid or a base. Here it's going to act as an acid and provide a proton to put on that oxygen. Not surprisingly, water is a little bit more acidic than most aliphatic alcohols. And that will give us the product. And again, you'll know how many times you have to show this based on the structures that you're given. But that will eventually happen 3 times for each trialkyl borane molecule, and you'll wind up with an inorganic boron species, which we're not so concerned with, and your alcohol product. So that's how you get the non-Markovnikov alcohol. And I cover all that here in the class notes. So yeah, that's basically it. And again, the reason that the oxygen goes on the other carbon than Markovnikov's rule would predict is because that's where the boron is. And the boron has to go onto that carbon by what we said before. The boron's going to go where there's more space for it. And the hydrogen in the more hindered or more substituted region. So no wonder that happens. It just makes sense that the bigger part of the borane molecule, especially once you start adding other spinach to it, but that the bigger part of the molecule is going to go where there's more space for it. Perfectly logical, I think. And you need to know that in order to know this reaction. Don't refuse to learn these details. They are the key to success. And I become more and more convinced with each passing year that it's the students who refuse to learn those details, refuse to even try, that have the most trouble. But if you understand that, then the reaction makes perfect sense. Of course the boron goes there. There's more space for it. A hydrogen atom is really small. It can get crammed in where there's less room. Not so much this part of the molecule. Good, but then not only that, we also see it's in this step over here that the carbon-boron bond becomes the carbon-oxygen bond in the alcohol. And if you understand that, that will help you to remember why the reaction goes the way it does. That's why the OH winds up on the other carbon than Markovnikov's rule would predict. Not because it's a rule breaker or an exception. It's not. It's a perfectly logical consequence of the mechanism. And understanding the mechanism will enable you to know what you need to know about this reaction. And once you understand it at that level, and you're not born knowing this, goodness knows, it takes some practice. But once you understand it at that level, it's not a matter of memorization. You just understand the reaction and understand that as a consequence of the mechanism, of course we're going to get the non-Markovnikov alcohol. And there's no carbocation anywhere along the reaction. If you look at the entire mechanism, this happens and then happens twice more. This thing happens, there's no carbocations yet so far, then it happens twice more, no carbocations. So no wonder we don't have to worry, we don't have to worry about Markovnikov's rule applying. There's no carbocation intermediate. And as such, we also don't have to worry about carbocation rearrangements because there is no carbocation. In the end, you wind up with the alkene being converted to the Markovnikov alcohol. And if you want to be very particular about the way this works, at first what happens is 3 of your alkene molecules add to a borane, and then all 3 of those alkyl groups that came from the alkene eventually come off and make alcohol molecules. So it's still a 1-to-1 ratio in terms of the organic pieces. Not like you suddenly made 3 times as many alcohols as you started with. In the end, each alkene molecule becomes 1 alcohol molecule. And again, the boron winds up in something inorganic, and as such winds up in the waste jug. But that's basically it for that. Good. Any other questions on this reaction? Just one last thing. You need to practice this. So remember, you're going to have to be able to show this, even if it's an alkene you've never seen before. So practice with other alkenes. Look at the addendum I gave to this chapter. Sorry. I'm sorry, H2O2. Over here, I put that H2O2 gets deprotonated and makes the hydroperoxide ion. And that's where this comes from. So everything shown needs to be shown. Anything not shown doesn't have to be shown. The reason, by the way, is H2O2, I don't have its pKa memorized, I think it's a little bit lower than that of water. Water is like 16. I feel like H2O2 is like 13 or something. You can look it up. But enough that the hydroxide ion is able to deprotonate to a reasonable degree. So that's where that comes from. Good. Other questions then? So practice, practice, practice. And again, in your Chapter 8 class notes, I gave you a method that you can use to learn what you need to know when it comes to learning reactions. And, you know, feel free to vary that a little bit to suit you. But in my experience, students have found that method helpful. So please take a look at that. Okay, well, as complicated and multi-part as that one is, hydrogenation of alkenes will be the exact opposite for us. And in the hydrogenation, you treat the alkene with hydrogen gas, generally one once in excess, and you do need a catalyst. Hydrogen gas by itself will not react with an alkene. Usually that catalyst is one of these coinage metals. Palladium is somewhere in the F block. And besides palladium, you could also put platinum, PT, or nickel, Ni. Any of those will work. You'll sometimes see PD/C. What that means is the palladium metal or the other metal is finely divided into a very fine dust that then gets adsorbed onto charcoal. So the C here literally means carbon. It means charcoal. And you can buy palladium adsorbed onto carbon. What that does is it increases the surface area of the catalyst and makes the reaction faster. The mechanism of this reaction is not well understood. Certainly, I don't know what it is. Your book does a hand-waving thing, and they try their best, but I'm skeptical. My understanding is that even the best minds still don't really know what this mechanism is. And if they don't know what it is, you can draw your own conclusion about whether you're going to have to know the mechanism. However, the end result is easy to understand. Each of the two alkene carbons, or rather the pi bond between the two carbons in the alkene, goes away and the double bond becomes a single bond, and each of the two formerly alkene carbons gets a hydrogen attached. That, of course, comes from the hydrogen. So this is very clearly and obviously an addition reaction. And in cases where there's a stereochemical issue, which again you'll mostly see with cyclic alkenes, what you'll find is that the two hydrogens wind up cis to each other. It's a syn addition, S-Y-N, not S-I-N, S-Y-N. And so you wind up with the two hydrogens being cis to one another in those cases where you're able to tell that they're cis because there's a stereochemical issue. In a standard acyclic alkene, you won't even be able to tell. But I have some more information here on the reaction. We'll also learn quite a bit later, maybe not, we'll also later learn quite a bit, that's what I meant to say, about redox in organic reactions. And we'll learn that this is a reduction reaction. And one of the ways that reduction reactions are defined, which we'll get to that point later, but one of the ways that we'll define reduction reactions is that you have more CH bonds, or it doesn't even have to be carbon, more bonds to hydrogen in the product than you have in the starting material. And we'll have 3 or 4 other similar definitions for oxidation and reduction. But I think you'll agree we have these 2 new bonds to hydrogen in the product that we didn't have in the starting material. So that's how you know it's a reduction. Let's see. Yeah, the H2 reduces only alkenes and also alkynes. I believe I already mentioned benzene rings. It's possible to reduce them, but it's much, much more difficult. You got to use much more extreme conditions. So I would say if you used hydrogen and palladium or platinum or nickel with styrene, which is vinyl benzene, it's benzene, then CH double bond CH2, it will only reduce the double bond, the carbon-carbon double bond in the alkene. It will not touch the benzene ring. And you'll wind up with ethyl benzene as your product. That's what I would expect anyway with this reaction. And the other things, we'll later learn that you can also reduce alkynes. That's, by the way, why I split up the material the way I do. I think exam 3 is going to be chapters 8 and 10, and trust me, that's enough. Just those 2 chapters is more than enough, as I think you're already learning about chapter 8. It's a sprawling chapter. Chapter 9 then is on alkynes. And one of the things we'll learn, there's other things that alkynes can do also, but one of the things that we'll learn about alkynes is they tend to undergo the same addition reactions that alkenes undergo, except they happen twice. And that makes sense. There's 2 pi bonds in an alkene versus only 1, 2 pi bonds in an alkyne versus only 1 in an alkene. So that makes perfect sense. So that part of chapter 9 is going to be relatively easy to learn. And that's why I put 9 and 11 on exam number 4, which is again going to be more than enough. Good. Oh, and again, multiple bonds from carbon to oxygen or nitrogen, and I already mentioned benzene rings. Those don't get touched. Those usually are at best much more difficult to reduce with catalytic hydrogenation. So you're mainly going to be looking for alkenes and eventually alkynes as the substrates for this type of reaction. And that gets us to between 11:15 and 11:20. Good. I certainly want to save epoxidation until next time. Maybe now, if you will, let's switch gears. And if you haven't already, please register your attendance. And let's look at the clicker session or reef session. Like I said, you'll just get 10 points for participating. But I have a little exercise for you guys, which is write the mechanisms of the following 2 reactions. And I would put it to you that if you can write this mechanism, which I hope you can, that would have been fair game even in exam 2. But if you can write this one, I would put it to you that we've already learned enough that you can write this reaction mechanism also. Anyway, this is what I put. So hopefully this first reaction is quite familiar. The first step is that our alkene pi bond swings out and picks up a proton from our HBr. HCl or HI would do the same thing. And we get our carbocation. In this case, that carbocation is tertiary. It's not going anywhere. That's not going to rearrange. It's already as stable as we can get. And then recall that your halide ion, which is now covered up by the thing, is simply attacks the carbocation and you get your product. So anything equivalent to that is fine. There's many, many other correct ways to draw those arrows, but anything equivalent to that would be fine. And as you might be able to tell, I literally copy and used my lasso tool and copied this, selected and copied it down here. The arrows are exactly the same, except instead of HBr, HCl, or HI, I've got a hydronium ion here. So if you know about this step, then you know everything you need to know to understand that step. It's the same type of idea. We'll take a proton from whatever our Bronsted-Lowry acid is. Now, I mean, we could address other issues. How do I know to use an H3O plus ion instead of a water molecule? Well, I think you'll agree H3O plus is significantly more acidic than H2O. And it wouldn't make sense to deprotonate water and get a hydroxide ion when you're in an acidic medium. Over our arrow, it just said H3O plus, so we know that we're in an acidic medium. We get the same type of carbocation. Now, instead of a halide ion attacking, we have a water molecule attacking. We've seen that before. We saw that in halohydrin formation. So, and again, the way I know not to use OH minus, which would, in theory, save me a step, the way I know not to do that is because I'm not given any. If you go back and look at what we had before, maybe I can do this, or maybe not. If you look at what we had before, it's only aqueous acid. I don't see any mention of hydroxide, so I can't use it in my mechanism. You have to use species that make sense according to what you're given. And all I see here is H3O plus. That means really the only species I have at my disposal are H3O plus and H2O. Now, of course, the way we got this was by adding a little bit of some strong acid. But if it's a strong acid like sulfuric acid or HCl, that's going to dissociate completely. So yes, there's going to be the conjugate bases of those strong acids, the chloride ion or the bisulfate ion floating around HSO4 minus. Those are just spectator species. They're not going to be involved in the chemistry. Anyway, that gives us this protonated species. If you go back again and look at halohydrin formation, you'll see we got a somewhat similar intermediate. And so the way we deprotonate it is by using a water molecule. And again, the way I know to use that is because I'm not given anything else that I can use to act as a base. That's the strongest base I've got around. So we'll use that, and that pulls off the proton, and you get the product. It's really the same mechanism, except that we have just this extra one proton transfer step. So I thought you would get more out of it working through that yourself to the best of your ability, and then us going over it like this. So this is already on eCampus. Clear all my drawings. So I mentioned about hydrogenation a moment ago. I said that, for instance, if you were to take styrene, styrene is vinyl benzene. I predict that if you treated this with hydrogen gas and palladium or platinum or nickel over charcoal, it will leave the benzene ring alone. And I think you would get ethyl benzene as the product. And I actually did a circle for the benzene ring. Even if you're a Kekulé structure person with the bonds, same thing. Remember, those are not really double bonds. Benzene is special. So that would be the product that I would predict. It would take much, much harsher conditions in order to reduce the benzene ring also. It's possible, but it's much more difficult. And certainly under standard hydrogenation conditions like this, I would predict with confidence that the hydrogen will not touch the benzene ring. Another example of a multifunctional compound, let's say that we had this unsaturated ketone, and we treated this with hydrogen over palladium and charcoal. And again, this could say platinum or nickel also. Solvents, suitable solvents for hydrogenation. I've heard of ethanol being used. It's generally something pretty polar in order to be able to accommodate all those nooks and crannies on the palladium on charcoal. I've seen acetic acid used. I've seen ethyl acetate used. So generally something fairly polar. In this case, I would predict that it would not touch the carbonyl. It would just reduce the carbon-carbon double bond, and you would get cyclopentanone. Oh, right, and just since we still have a couple minutes, I think I'll even still be able to let you out a little bit early. I mentioned about alkynes. Well, 1, 2, 3, 4. We'll call that guy 1-hexyne. How does that sound? If we used an excess of hydrogen, or at least you could also write 2H2, same thing. We would need at least 2 mole equivalents with our palladium on charcoal or platinum or what have you. I would predict that we would get hexane out of that. It would reduce the triple bond all the way to a double bond, all the way to a single bond. 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yep. And so, which begs the question, can you stop it and get an alkene? You can. We'll get to that in chapter 9 when we finally get there. But this is why I was saying for all those alkyne addition reactions we get to in chapter 9, you already know all you need to know about them. They do exactly the same thing as alkenes, except they happen twice. Yes? What, sorry? Excess, EXC period. Or you could put 2H2. That's also acceptable. You need at least 2 mole equivalents to get rid of the triple bond. Because if you used any less, you'd get a mixture. You'd get some of the alkane, some of the alkene, and some unreacted alkyne. So you do need to use an excess. Oh, I think I thought it for a moment. I lost my microphone, which I'm just glad the microphone lasted this long. I'm pretty much out of time anyway. Any last questions? Good, that's actually a good place for us to stop. We'll pick this up on Monday with oxidation and cyclopropionation reactions. Have a good weekend, and again, please stop by and get your exam if you haven't yet. Is this week the bye week, or is that? And I think this week is the bye week, because we're not done with chapter 8. Update on exams. They're hard at work. I think we'll be able to make our goal of handing them back in class on Wednesday. Bye week from OWL. Football, I don't know about.